So in this lecture, the discussion is about process synchronization and the issues in process synchronization. So whenever two processes they do not depend upon each other's execution, then we call such processes as independent processes. On the other hand, when we consider the processes which are sharing a common space or a variable or a memory, then such processes are known as cooperating processes or dependent processes. So in case of where the issue occurs, in the sense it occurs usually in cooperating process, that is whenever we share a common area, that is if process that is executing in its own memory space, there will be no dependency between any other process, and there is no correlation between their execution. But if suppose both are interacting a same shared variable or a same common memory space or a resource, so in that case the many issues may occur. So such may conditions they may lead to process synchronization issues. So this is a diagrammatical representation in where two process P1 and P2 are executing, and these two processes are sharing a common variable called as count. So from this diagram you can see this is the A and B are the local variables of the process that belongs to the process P1, and X and Y are the local variables that belong to the process P2. So these variables they will be executed, or the code of section which are not shared between these two processes, they will be executed in the non-critical section, whereas the shared variable, that is here in our example the variable that is shared between these two processes P1 and P2 is the count. So this count variable, this segment of code, it should be executed in the critical section of both the P1 and the P2 process, so that the at the same time it is not given the permission to update its value. So this is the main reason why we execute the shared variable in the critical section, right? So this is a real-time example that shows how process synchronization may lead to some issue. That is, imagine there are two boys, assume a boy and a girl, two persons are about to use the restroom for changing their dress. So initially the room is vacant. So first when the boy is inside, the girl cannot definitely the girl cannot enter the room, so she has to wait outside, so until the boy returns back. So at the time in this room only one person will be allocated, so only one person can take the room for processing their task, right? So this is one real-time example of process synchronization. Okay, so such issues that may occur due to sharing of a common resource or or a variable, at that time we call that condition as a race condition. So whatever we have discussed so far, so in at that time the same process, there is two process, they can't access the same place over and over again at the same instant of time. So if suppose if it happens, then such a condition is called as a race condition. So let's consider two processes which share a code as given here. So by the way we see, we can easily interpret that in process P1 there is a variable called as A, and in process P2 there is a variable called as B, and these two processes are gonna share the variable share, that is they are going to coordinate between them by using this common variable called as share. And initially imagine that the value of share is 5. Okay, in our example let's consider that the value of share is 5. So initially for this local variable A we assign the value 5, and then I'm incrementing A to 1. So definitely now the value of A, it would have been updated from 5 to 6, right? So now the system goes to a sleep state for about 1 millisecond. So at this time, please listen, at this time it is not possible for the CPU to make any sort of execution, because we have called the sleep command, which will make the process to go for a rest for a specific instant of time, right? So at that time we cannot let the CPU to sit idle, because as a good programming practice is to have the CPU, the throughput of the CPU as 100% throughout our process execution, right? So when this command executes, so definitely I need to make the CPU to run some other process. So now there will be a context switching from P1 to P2. So when this, after execution of the sleep command, the system will be shifted to the process P2, and the CPU will take the hold of the process P2, where it initializes the value of share, that is, which is nothing but 5, because that was the initial value. So the value 5 will be allocated to B, and here we are decrementing the value of B. So sorry for the case insensitivity problem. So actually it is case sensitive, so b minus minus. So now I am decrementing the value of 5 to 4. So at this stage the value of b is 4. Again in process P2 also we are letting the process to call the sleep command for 1 millisecond, right? So again when this command gets executed, once again the CPU will make a context switch by to process P1 by storing all the updates of the process P2 into the PCB, that is process control block, right? So now the value of A it is in the incremented state, that is from 5 to 6 it has incremented. Now after incrementation, now I'm storing the value of A, that is the incremented value, which is 6 to share, right? Now at present the B's value is 4, because it has decremented to 4. So once after the completion of P1 process till share is equal to A, now we will be again executing share equal to B. So now the value at the end of this process P1 is share is equal to A, which is share is equal to 6. Okay, but now after the completion of share equal to A statement, the process again it will be shifted to P2, and now the B's value, which is 4, the decremented value, it will get allocated to share. Okay, so share is equal to, it will be over returned, that is the value of share, it will be over returned to from what value to which value, from 6 to 4. Actually initially the value of share is 5. So if we increment the value by 1 and decrement the value by 1, automatically we act as per the rule of mathematics, we need to get the value of share as 5 alone, as 5 only. So there should not be any change in the value, that is incrementation and decrementation has happened only once. So definitely shares value should be the same, that is only 5. Okay, but actually what value we are getting at the end, share is equal to 4. So definitely it is a inconsistency. At this state the data has become inconsistent. So such a condition is called as a race condition. Okay, so in order to avoid this race condition problems, there must be a synchronization between the processes which are running concurrently. Okay, so we need to avoid the inconsistency in the data. So that is why we go for the process synchronization. We go to solve the process synchronization issues. So how can we solve this? So this can be solved by executing the shared variable, that is the variable or the memory or the resource which is shared among two or more processes, by having that particular segment of code in the critical section of every process. Okay, so there is a segment called as a critical section, there is a section called as a critical section, where the shared variables are allowed to be executed. Okay, so let's consider process P1, P2 up to Pn. So each process they will be having a segment of code which is allowed to be run only in the critical region of that particular process. So when we update any changes, when we make any changes to that shared variable, that can be reflected only once by any one of the process at one instant of time. So such a section is called as a critical section, right? So only one process will be allowed to enter into the critical section at one particular instant of time. So no two processes can be entering into their own critical sections at any common time. Okay, so this is what a critical section is. So this is how we diagrammatically represent how a critical section looks like. So here we write a do while loop. So before the critical section we have an entry section. So first of all, each and every process should make a request to enter into this critical section. Only if the request is granted, they will be entering into the critical section and they will be updating the shared variable here. right? So once after entering into the critical section, if any one process, for example, imagine there are two processes P1 and P2. So if P1 has entered into the critical section, by getting the request from the entry section, we will just close the door, right? So we will not allow any other process which is presently ready to to get its execution in the ready queue to enter into the critical section, right? So such a section is called as a critical section. So once after P1 is has finished its updation of the shared variables in the critical section, it will be allowed to exit. So while exiting from the critical section, all the other processes which are waiting, they will be getting a signal that the process P1 has completed its execution in the critical section, and so now you all can enter into any process can enter into the critical section for its execution. So likewise, as a bouncer, okay, it is giving a protection to the shared variables present in the critical section. So this is how the code looks like. A critical section code looks like. So there is an entry section, a block of code which is executed for the preparation. Only a request will be granted only if there is no other process in the critical section. A request will be granted to any other process, and the exit section, the code executed upon leaving the critical section, every process will execute this exit section code, and this will give us the signal to all the other process. And the reminder section, whatever code is present in the rest of the program, they are placed in the reminder section. Okay, so the solution for this critical section problem, it can be any solution that is given to the critical section problem, it has to satisfy these three conditions. One is mutual exclusion, and the next one is progress, and the other one is bounded waiting. So mutual exclusion, so as the name indicates, mutuality, only one process it can be allowed to enter into the critical section at any instant of time. That is called as mutual exclusion. So similar to an atomic property, okay, at a time only one process is allowed, so that is called as mutual exclusion. Okay, so what is progress? So progress is nothing but imagine there are n number of processes available in your system, and every process, once it gets its entry into the critical section, it will not allow any other process to enter into its critical section. That's what mutual exclusion is, right? So at that time, the progress of one process, it should not affect the progress of any other process. Only then we will have a we don't have any process synchronization issues. That is known as a progress. And bounded waiting, so if suppose process P1 is holding a resource that is needed by the process P2, and P2 in turn is waiting for the resource that is needed by process P1. So one on the other hand, both the processes are dependent on each other for a long period of time, they have to wait. Okay, so such case is called as a bounded waiting, and this should also not happen in any system. So only if a solution it satisfies all the three conditions, we can be sure that the critical section problem will not occur. So this is known as the solution to critical section problem. So these are the explanations that are given here. So mutual exclusion implies only one process can be inside the critical section at any time. Okay, so this is made the proper execution of this mutual exclusion is conducted by using the entry and the exit section, as we have seen in the earlier slides. And the progress, so one progress should not stop the execution of the other process. Okay, so only then the progress will be in a smoother manner, right? So bounded waiting means each process must have a limited waiting time. So for a long period of time we cannot let any process to wait, so that the process execution it won't happen. It leads to a synchronization issue. Okay, this should not be happen. So these are the different solutions for any critical section problem. So the continuation of this lecture we can see in the next session. Thank you.